Our next session is our keynote, and we're very happy today to have Paul Sathre from Virginia Tech giving our keynote. I'm going to give just a quick introduction. Paul has been one of the early adopters, like some of the speakers in the previous session, who've been kicking the tires on our GPU features and giving us feedback on it. I was checking my notes this morning. I couldn't find a firm date quickly, but it feels to me like it's been about a year and a half or so. And so over that period of time, he's been able to see the progression from kind of the very earliest days that we're starting to roll out GPUs to where we are today. And I think that's been nice for us in terms of, not just having that sort of single point in time and reaction to that. Paul's a research software engineer at Virginia Tech, and I think this puts him in a really unique position in terms of being at a high-class institution where he's following sort of current trends and current tech and things like that. But yet, at least as I understand his position, I can imagine that he has maybe more of an applied or practical mindset than that of a typical academic researcher. Not to put down typical academic researchers, but I think that aligns well with kind of our Chapel attitude of kind of get it done. Like, it's not about necessarily always publishing the papers or anything. It's like creating something that's useful and usable. And so we really appreciate Paul's perspective from that, for that reason. Personally, I'll say I think Paul's kind of one of my, he sort of has a lot of the qualities that I picture in an ideal user. He's very communicative, very helpful, resourceful. He doesn't just sort of flail and sort of wait for you to solve everything. Like, he's very good at helping himself as well. Not at all shy to let us know when we've gone wrong, which is very beneficial sometimes. And also generous with his appreciation when things are fixed, which is nice. And I think best of all, it seems he's the kind of person who won't, or at least hasn't so far, just stomped away at the first sign of trouble. Like, he sort of grits his teeth, gets through it, and sticks with it. And that's been really helpful as we've worked through some of those challenges. For those of you who were here last year, Paul gave a great talk at CHU 2023 on our survey results. A lot of people called it out as one of the highlights for them. It seemed therefore natural to invite him back to give the keynote. And with that, I'll turn it over. His talk is entitled "A Case for Parallel First Languages in a Post-Serial Accelerated World." Paul, it's all yours.
All right. Thank you, Brad, for that introduction. Yeah, I'm a little bit more of a low-level code guy than a higher-level guy, and that does give me a perspective on drilling as deep as I need to find the answer to a problem. But sometimes that it's a little more stubborn than my boss might like. But anywho, let's get right into it. So before I start, I'm going to poke at a couple technologies here and there. They're great technologies. They've gotten us to the point we are today. And we should be proud of all the serious science we've done with them. Don't let critical feedback diminish that prior art. That's not what I'm trying to do at all. It's just by building on the shoulders of giants, we can look forward and think about how we might do things better going forward. This is also my talk. Sometimes I come off a little snarkier than I might intend to, so if that happens or I have a technical omission or something, let's talk about it at the break. Please don't send my boss, my coworkers, my employer a nastygram about it. And then finally, I am going to use a couple product logos and stuff. Obviously, those belong to their respective rights holders, so they're neither endorsing this talk nor am I necessarily endorsing those technologies. It's just a good way to talk about the things we use to get our job done. And so since I am kind of new to this community, I wanted to give a little bit of background about me and where I'm coming from. I promise this is not going to be a 50-minute ego talk, but to let you know my background, as an undergrad, I went into Virginia Tech with a high-end desktop for coursework. And it had a quad-core 64-bit AMD when 64-bit was still kind of new, and a NVIDIA 8800 Ultra GPU, which happens to be one of the first CUDA-capable consumer GPUs. But it also had this little lesser-known card called an AGEA PhysX processing unit. And I only bring that up because it's kind of a sign that even before I had any formal HPC training, it just intrinsically made sense to me that if you had a difficult computation that you did often enough, you might want to offload it to a purpose-built piece of hardware. So I was coming up during the time that Roadrunner was just coming online, so I had some friends with PlayStation 3s, and I would eventually join a lab that had access to about 20, maybe a couple more, that they were using to figure out how to program the Cell broadband engine. And so I fell in there and briefly did a stint of bioinformatics on something called the Telera Tile 64, which was a mesh architecture, good, tight interconnectivity between 64 cores. Then I fell into a comfortable groove with GPUs via OpenCL through 2 summer internships at Los Alamos. For my grad school, I sort of broadened my scope towards more portability and interoperability. by doing a thesis in CUDA to OpenCL translation. And then shortly after that, I extended to OpenMP and MPI to do this 3 languages, 3 hardware sort of interoperability tool for some CFD codes. But since then, I've focused more on the productivity side of things. I did a couple tools for OpenCL support for FPGAs because OpenCL, though it may seem low level to some of us, is a much higher level approach than VHDL for programming those reconfigurable architectures. Then I looked at SYCL because modern C++ semantics of that built on a lot of the lessons from OpenCL, and I used that for GPU and then FPGA for a couple years. But now for about a year and a half, closing in on 2 years this fall, I've been using Chapel because it's got GPU support now. And we're very interested in anything higher level than the OpenCL that most of my career has been built on. And so I've been looking at performance productivity trade-offs similar to what Josh and his group have been doing. And now moving into some partitionability questions. And hopefully I'm going to get to do some portability work in the near future. So that's a little bit about me. But what I really care about, in summary, is closing the gap between the parallel hardware that we already have and people who could benefit from it. So that kind of supposes these 2 questions at the bottom is how do we enable that? And conversely, what are the barriers to doing that? So to give you a preview of what today is going to look like, it's kind of modeled on a typical play in 3 acts. First, we're going to talk about parallelism and how it's everywhere, and we should kind of start acting like that. Then we're going to talk about the rise of GPUs up through sort of the modern day. That's what I know the best. And then I'm going to kind of give my idea about how Chapel could fit into GPU's future, and in turn, how us as members of the Chapel community fit into Chapels. So that's what we're going to do. And before I get right into it, since this is the first ChapelCon, I wanted to look back at some of the 10 prior Chew keynotes and see if there were themes that still resonated with what I was going to talk about today. And I was pleased to see that even at the first one, long before I joined the community, GPUs are already mentioned. We see a recurrent theme that Python and interactive development flows are important, and keeping compiler turns and analysis turns within the human thought loop. We also occasionally see this conflict between these large FANG or DOE, DoD scale frameworks that sometimes can be difficult to prototype in and scale down, contrasted with laptop scale tools like R and things like that struggle to scale up. So maybe Chapel could fill that middle ground between these 2 scales. We also see the importance of analysis, viz, packaging, and aligning to where the community is more than expecting them to align to where you are. That's something I'll touch on a little bit in Act 3. Of course, we occasionally see, as we saw in last year's keynote, that PGAS in the right circumstances can beat MPI and other explicitly distributed solutions in the right circumstances in terms of productivity and network performance. But as always, flexibility and performance are more important in an HPC language than transparency. If we are able to give users a high-level thing, that's great, but never take away their ability to do something nifty and cool and high performance if they need to. But if you can smooth that ramp out, like Chapel does in a lot of cases, that's a really good thing. So with that, I'm going to take a sip of water and we'll get right into Act 1. So parallelism is everywhere, so I think we should start acting like it. If you've been in HPC for any stretch of time, you've seen a graph like this over the past 10, 20, or 30 years. And what it's really showing is that our transistor counts keep increasing, but our single-threaded performance and frequency have pretty much stalled out. So we've compensated for that by increasing the number of logical cores. But I want to highlight basically where my cohort, plus or minus a couple years, started on parallel processors. We've never programmed on something that was serial, and most of the generations to come never will. So we've always been on parallel hardware, and the serial performance has barely improved since I started. So parallel hardware was already common when I came in, and now it's pretty ubiquitous. You really have to struggle to buy a laptop or a cell phone that doesn't have at least 2 cores and a handful of accelerators. So HPC moved on to parallel and distributed a long time ago, but those 2 things are still not very general yet. And of course, as we saw in the previous session, hardware is also heterogeneous, but we're just going to put a pin in that. We'll revisit it more in Act 2. So we moved on to parallel, distributed, and heterogeneous a long time ago. But the reality is nobody starts their programming career on an HPC cluster. Many programmers never use a cluster computation. And everyone starts on a laptop or a desktop. So I wanted to take a look at what regular users were using. And to do that, honestly, the first thing I thought about was the Steam hardware survey. If you're not aware of what Steam is, it's a gaming front end. And every month they send out an anonymous survey to all of their users. Well, not all of them, some percentage. And you can choose to just submit your hardware specs. It takes like 10 seconds. So what this captures for me is a rough proxy of general purpose hardware. It's the stuff that's affordable for hobbyists, tinkerers, and undergrads. And some of them might, go on to become future HPC buyers, but this is what's in everyday households. And while you can't see it on the list, the April statistics do have 0.05% single core machines still reporting, but pretty much everybody has between 2 and 10 cores. They tend to have 16 or 32 gigs of RAM, and in summary, about 92%, just about two two standard deviations, have between 4 and 16 physical CPUs and between 4 and 32 gigs of RAM. That's a typical system today. And they also report vendor statistics for GPUs. And as we might have expected, NVIDIA is far and away the market leader for gaming GPUs, but AMD and Intel are represented. And before we move on, though, I do want to note, they expose the individual device names in the survey data. So I was able to reconcile that against NVIDIA's CUDA-capable GPU list, as well as AMD's ROCm-capable GPU list. So we'll come back to why that's important in Act 2, but I just want to note that 68% of respondents had a CUDA-capable GPU and 0.38 had a ROCm-capable GPU. So with that in mind, to me, as somebody who's been doing HPC in the small for a while, I think it's changing, it's broadening. And even before the pandemic, we had a trend that users and developers were becoming more mobile and remote. We were switching to open office plans. There were less of a chance that you get a dedicated cubicle with your own high-powered workstation, and a better chance that you're going to get a company laptop or maybe even a bring your own device situation. And along with that came some shifts in IT trends too, where individual developers are picking the tools that work best for them. It might be VS Code, it might be a bigger editor. We see a lot of Notepad++. I'm a Vim user still. So there's this piecemealing of different tools that fit the individual workflow. We also see, of course, as we saw on the previous slide, multi-core and GPU at home. Everybody wants to be a streamer of some sort, it seems. And then in the business side of things, it's not just privately owned data centers. There's a lot of companies that are serverless and using infrastructure as a service, and they just rent the cycles they need rather than doing a big iron capital expenditure. But in the small scale, anybody that wants to and has a credit card can rent some AI cycles. You can buy time on an A100 if you want to play around with that. So to address the laptop and the home and the infrastructure as a service data center, we need a unified approach to programming all of that, not just the CPUs, but the GPUs, the network cards if you're doing distributed, and whatever hardware comes next. There's probably going to be some tensor cores, but something cool will come out after that, as we've seen. So the hardware side of the equation, I think, is kind of solved. Regular users have or can get parallel hardware. So then maybe it's the parallelism itself that's hard to understand. But reflecting on that, I'm not sure that's true, because the real world that we live in every day is massively parallel. And as humans, we experience that in our day-to-day life, whether we're noticing it or not. If you've seen bees, you've seen scatter-gather. If you've watched a nature documentary and seen the schools of fish for a flock of sheep, you've seen something that looks a lot like single instruction, multiple thread, as the fish get chased by a dolphin or the sheep get chased by a sheepdog. You've been to a grocery store and the lines have backed up and a new cashier opens another lane. A couple carts filter over there. That's task parallelism and work stealing. And of course, if you've driven or ridden in a car, you've pretty much run the gamut. You've done pipeline parallelism on an interstate. If you've been through a toll booth, you've essentially done a memory fence, because it doesn't matter what order the cars in various lanes go through. On one side, you've got cash, and on the other, you don't. And if you've done a red light, well, congratulations, you've successfully negotiated a semaphore. So these parallel things are things we experience every day. And we've got hardware, but if you go to the programming subreddits, which is a place I lurk sometimes, it still seems very hard. And I'm left to think that it must be because we're teaching serial first, and we're using existing post-serial languages to do it. And what I'd like to see is, because reality and hardware are parallel, I want to move the teaching towards that direction, because even serial threads don't run in isolation. That's sort of a lie we teach. And this is more asynchronous than parallel, but the OS can deschedule you. Your USB can get unplugged. Your network connection can go down. life can happen while you're doing this serial computation. And rather than teaching students to not know about that, I think we need to teach them how to be safe and effective in a parallel and concurrent and asynchronous world. Because we don't teach new drivers that they're the only car in the interstate. That's not safe for them or anyone else. We teach them how to do defensive driving, and I think we need to do the same thing for our new programmers by giving them thread safety and fault tolerance tools. If your algorithm truly needs a critical section, I'd never want to take that away from you, but I think it should be the exception rather than the norm. And I also think that we need to move these concepts earlier and teach them to more of our programmers. At VT, parallel computing is a 4,000 level, senior level elective. So as an elective, not everybody takes it, and it's after a 3-course sequence taught in C about computer architecture and operating systems. So by that point, any serial habits have already been anchored by 3 years of instruction. But if we really want to move parallel education earlier, we need a language that is easy, parallel first, and general. And I'll talk more to what I mean by parallel first on the next slide. But I do think PGAS could be a good approach to teaching distributed, because network programming is still an important concept and it underlies PGAS. But when we're doing a cluster computation, we're not talking to a node that's halfway on the route around the world most of the time. It's, you know, four U's up or 2 racks over. We don't need to do the equivalent of like addressing an envelope and putting a stamp on it. We can use a whiteboard to talk to a coworker that we're co-working with, right? And I think PGAS has a model like that. It's just some cores that are a tiny bit farther away and have a couple additional failure modes. So to drill closer on what I mean by parallel first languages, I want to contrast them against what I call post-serial, or serial with sprinkles if I want to be a little bit snarky. And what I mean by that is optional libraries, pragmas, or language extensions. They're things that are sprinkled on top of an existing serial language. So CUDA, HIP, MPI, OpenMP, OpenACC, OpenCL, SYCL, thread building block, Silk, standard PAR. If it's built on top of C, it's fundamentally a post-serial sprinkle. It's an optional feature. And I think what I found in Chapel is a different option, and that's what I refer to as parallel first. It's having the parallelism be a non-separable part of the keywords, data abstractions, and semantics of the language. And array promotion is a great example of this. It's just there. It's not hidden behind an extra library that you have to add in. It's just there. And I think that matters for both philosophical and technical reasons. On the philosophical side of things, I think it's important that we gradually realign our languages to the hardware we actually have, and in doing so, demystify parallelism. It's a complicated concept in computer science, but it's really just a set of rules and tools for how you get correct results out of the hardware we actually have today. On the technical side of things, though, I think when you're implementing a language, a runtime, a standard library, or just a code in a language, there's 1,000 little micro decisions that go into how you're designing things. And if you know that parallelism can happen when you're doing that, those 1,000 little decisions all add up to a built-in better parallel safety than tacking something on after the fact. And we see this in the other technical point with some of the existing post-serial solutions is sometimes the base language and the solution evolve asynchronously, and that can cause conflicts where you have to either use parallelism or you get to use the new features. And we saw that with OpenMP. Until the 5.0 spec, it didn't formally support C++ newer than 98. And the 5.0 spec came out in 2018. Now, you might have been able to use modern C++ features on, depending on whose compiler you use, but formally that was unspecified. And there's still things in 5.0 today that you can't do in C++ 11, 14, and 17. So you're forced to make this trade-off between the new, syntactic wonderfulness of the modern versions of the language or your parallel extension. And when you have a parallel first language where it's baked in, there's less chance for that conflict to happen because the parallelism grows with the language, not asynchronous from it. So to start wrapping up this act, though, I do want to look at a vector add, and we've seen some of those examples like this with Stream in Josh's talk earlier. But I want to pick at this question of whether or not with vector add we care about the individual element's experience, because a vector is really just a linear collection of things. And if we only cared about an individual element, we could express it as a scalar, but we're choosing to express it as a vector of related things. And of course, if we write a serial program, well, that's what we have to do. We have to iterate on every element in the vector. And if we use a post-serial model like OpenMP, we keep the serial portion and then sort of invalidate it a little bit by providing this pragma that says how you're going to parallelize it. So the extension and the serial language are directly in conflict right next to each other. And of course, we can say this in Chapel we can talk to each individual element's experience if we need to. Some of the code I've written has required that. But I think as a collective operation, we care more about the vector as a whole. And that's one thing I really have liked about Chapel is with array promotion and some of the other built-in language features, it better matches our mental model of what we actually want to do, which is add these two collections together, not so much caring about the individual elements in it. So that brings us sort of to the end of Act 1. I'd like to briefly collect our thoughts. So I've shown that the world and modern hardware are parallel, and I really think it's high time we started acting on it. It's kind of too late to catch most of my generation, but the next ones to come and the one after that are probably going to be programming on parallel hardware. So I think we need to start pushing that far earlier in the curriculum and teaching it to new users. And I think as part of that, we have to change our mental model of computation from this single-threaded hero's journey to something more like shepherds, steering the flocks of threads to their correct destination. But of course, I have a GPU background, so we do have to talk about that. And that's going to be the subject of Act 2, the rise of GPUs up through today. So hardware is parallel, but hardware is also heterogeneous. Even before my time, we had discrete floating point units, and they eventually got merged to the CPU, but we've also got graphics and physics and signal and crypto and tensor and data and vision and reconfigurable and neuromorphic and a whole bunch of interesting processing units. And some of those will end up ultimately getting married to the CPU, as we're seeing with Grace Hopper and the MI300As and some of these FPGA architectures, and some of them won't. But if we look at hardware that's in, say, our top 500 systems by performance share, yes, there's a significant portion of this that is still homogeneous systems. But if you look from 2004 all the way up to last November, we can see a trend that year over year, the flagship systems keep being built on heterogeneous hardware. And occasionally there's pushback from systems like Fugaku, but there's a clear trend here towards increasing heterogeneity. But there's also a clear trend that the accelerator and language of choice keep shifting. And so in line with that, a lot of my career is focused on portable approaches to programming GPUs and other accelerators because I think they're necessary to reduce how much rework we're doing. We're spending millions of dollars translating code for each new generation of supercomputer. But if we look at the November list, 70% is GPUs. 70% of the performance share is GPUs. And split out by vendor, about a third of them, a little over a third, are going to be running CUDA. And about a quarter are going to be running HIP. And a little under a tenth are going to be running SYCL in the form of data parallel C++. And then the remaining homogeneous 30% will be using some CPU abstraction. So there's fragmentation among the languages here. And I want to look back farther on the side of the GPU languages. And so I'm going to try to give a brief timeline of what that looks like from my perspective. And as the keynote, I'm going to use my prerogative to say that anything before my time was the dark ages. There were approaches like AMD Close to Metal, Brook GPU, and heroic work to do scientific computations and graphic shaders, but times were pretty rough. And then we got CUDA, and it's been consistent year over year, advancing the language as it goes. Shortly thereafter, we were followed by C and Pragma and C++-driven approaches. And then most recently, in 2016, we get AMD HIP. And that sort of brings us up to date with the main GPU languages today. They all have modern versions. They're all still cooking nicely. And of course, if you need a distribution, just sprinkle a little MPI on top. It's fine. But alongside this, we had Chapel. It started back in 2003. You've all heard this story about the DARPA HPCS program. And for the first many years, it focused on CPU and distributed parallelism. But around the same time that these open GPU languages started coming out, people started using C interoperability to bring GPUs into the fold with Chapel. And many of these authors down below are still valuable contributing members to the CHU and ChapelCon communities. We just saw a talk that used GPU API from Georgia Tech. But it's really only in the past 3 to 4 years that Chapel has had official, built-in non-sprinkle GPU support. So it's an older language, but the GPU support is the youngest of all of these, and that gives it the advantage of being able to learn from all the mistakes and successes of previous languages. And so I do want to briefly highlight some of the things that I think CUDA did successfully and has led in part to them being the current market leader. The first of those is that consistency is king. They picked a model, they stuck to it, and when users or their architecture demanded it, they iterated on it, right? Users wanted a thread fence, so they gave it to us. They added tensor cores, so now they're exposed through CUDA. And in doing so, over 17 to 18 years, they built and kept a very deep knowledge state. You can still today see forum posts about CUDA 0.9 or whether OpenCL 1.0 is going to overtake CUDA 3. They also consistently and very successfully, I think, reached into the university programs by providing free training in GPUs. I attended one on campus at Virginia Tech, and most of our lab's foundational GPU work used donated consumer grade, I think, GTX 280s. So they reached people before we learned something else. They've also consistently given away their tools. There was never a complicated like license server that you have to email somebody your MAC address and get a free license. It's just a binary file that you can install and use from the data center to your laptop. And they eventually extended that to Debian and RPM installers and Docker pods and all sorts of other ways of installing the tool. They've also consistently been good at welcoming the small fish. They're not just focusing on data center or workstation GPUs. They're treating gaming GPUs and laptop GPUs just the same. And I think that's very important because by casting a wide net, that's where innovation happens. It happens in that froth of hundreds of thousands of individual users coming up with ideas and then consolidating around the ones that stick. So this is why, if we'll call back to Act 1, having 68% of gaming GPUs on Steam survey matters because those users can play with CUDA-driven AI workflows or other CUDA-driven processes today on the hardware they already have. They don't have to try to rent data center cycles, but they can. And then, of course, as many of us in the community know, NVIDIA is very willing to drive the conversation. They started the GPU Technology Conference, and early on in GPU trends, they showed up to every major supercomputing BOF with their decks in hand and knew how to, show what they were good at to people. So that's a very important part of drawing attention to a language. But if we zoom back out again, throughout GPU's history, you've always sort of had this pick 2 of 3 problem. You've got to pick between performance, productivity, and portability. And ideally, we'd be right in the middle, but I think we're still kind of trying to seek for that. On the performance side of things, that's where the vendor-specific languages tend to lie. And then the open standards tend to trend towards the portability and the performance, but anyone who's written a lot of OpenCL can tell you it's not the most productive language you could use. Now, OpenMP is closing in on the center here. The pragmas are very attractive. And then, of course, in the 2020s, you can't really avoid talking about Python, and we're going to mention it more in the latter half of this talk. So as we go forward, I want to think about where we would each place Chapel in this Venn diagram. I've got some ideas, but I haven't firsthand gotten to test much of the portability work. It did take a long time to get a driver for my 7900 GPU, but I'm part of that 0.38% that have a Steam and ROCm capable GPU. And the talks in the previous session did a good job of addressing portability. So I'll let them take the credit for testing that. But to start wrapping up this section, I want to revisit our vector add example because with my experience of GPUs, you kind of have the choice of languages between concise but implicit or explicit but verbose. And on the first side, I think that's where OpenMP4 and beyond fit. It's still a very similar loop to what we saw in the CPU, but as you can see here, and as Josh showed, with the I think that was tea leaf or stream example, the pragma has gotten a lot more complex, and each one of these new clauses has a very important implicit meaning to how the threads map down to the GPU hardware. And if you don't get that right, you might not get the performance you'd like. So it's very concise, but there's a lot of implicitness baked in. On the flip side, though, you're not necessarily supposed to read these because they're very small. But the CUDA, SYCL, OpenCL, more traditional like low-level GPU languages are really explicit. Every single line does something, and you can tell what it does. It allocates memory, it transfers memory, it launches a kernel. And there's some of it on the OpenCL removed here by a tool I wrote, but they're very verbose. There are more productive ways we could program GPUs than this. And I think that's one of the things, having used Chapel for about a year and a half now, that I'm most excited about, because I think it allows you to do both. And that's really what we're looking for from a higher level language. The conciseness gives you productivity, and the explicitness gives you maintainability because there's less arcana in what each line does. You can parse it more easily. And to show that by example, obviously this example is a little bit longer than the OpenMP, but it's very clear. You enter a GPU scope, you select the 0th device, you copy initialize some arrays from the host, you allocate an output array without initializing it, and then you use that collective promoted GPU vector add right here. You copy some data out, and then, like we expect of more modern memory managed languages, your buffers are just cleaned up for you when you leave the GPU scope. It's all very crisp, but explicit and understandable. But of course, vector add it's a pretty simple example. So we tried something more difficult. And as Brad mentioned, this was the topic of my Chew Talk last year. So I'd invite you to go watch that video if it piques your interest. But essentially, we took a graph workload called edge-connected Jacquard similarity, which is essentially the intersection of two vertices that are connected by an edge in their one-hop neighborhoods over their union. And you just apply it to every pair that are connected by an edge in a graph. So it's an order E set intersection problem. And it wasn't trivial. We had two different kernel pipelines. We had 3D kernels, which relate to the 2D T-leaf kernels that Josh just presented. And we had to linearize our ID space just as they did. And we had to deal with some atomics that weren't initially supported by Chapel, but were quickly added by Andy and Engin. And it also, as a graph problem, has essentially random access memory. It's not trivial. And as of my most recent line counts in, I think, January, our Chapel version has less than half the bulk of our CUDA version. That's a really significant savings. And when we were doing this work, we were fully prepared to have a performance hit. But what we found was it really was not that bad. I won't bog us down with the details of the 18 graphs. They're in the appendix if you're interested. But we went up to about 500 million edges and all sorts of different density ranges. And what we found was that the Chapel was anywhere from about half as fast to about twice as fast as CUDA. And we weren't expecting any speed up. So that was a pleasant surprise. But our geometric mean was a more reasonable 87%. So we traded 13% of our performance for half of our code. And that's a trade I would happily make again after many years in the trenches with OpenCL. So that gave us the confidence to work forward on a partitionable multi-GPU, multi-locale version of this that is still ongoing. We've got some IO stuff to work out. So in my experience, as a language for GPU kernels compared to the multitude that I've written before, I think Chapel's pretty good. It's productive, I think it's more maintainable, and the performance is similar and continuing to improve release over release. But given the context of what some of my lab mates are working on, I'm not sure that low-level kernel languages are where most GPU users are today. So I looked at Google Trends for essentially the 5 languages we've been talking about so far, and as we might expect, CUDA in the green here is far and away the market leader. What I wasn't I was a little surprised to see, though, was that OpenCL and OpenMP in the yellow and purple here are kind of on the decline. People seem to be gravitating away from C and pragma-driven models and towards modern C++ semantics like SYCL and ROCm. But this is just, post-serial GPU languages. I wanted to zoom out because I think Chapel is trying to be higher level than that. And a lot of our lab is using Python with libraries. And if you're talking about high performance Python, I don't do a lot of it, but our lab does. You really can't get away from talking about NumPy. And it doesn't support GPUs itself, but there's this project called CuPy to provide a compatible API with GPU support. And it's too new to render here, but it is growing and something that I think we should pay attention to. But what really interested me is that TensorFlow here in the purple briefly surpassed CUDA and is now pretty much tied with it. And PyTorch has rocketed past both of them. It's now competing with NumPy, which has been around for literally a decade longer. for, interest on Google Snapshots. So there's a lot of energy here. And of course, there are attempts to make some open standards like the Open Neural Network Exchange. And they sort of follow trends, but they're competing with a lower share. So with that in mind, I want to start wrapping up Act 2 because we're going to talk about what this means for Chapel in the next act. So to summarize, our GPUs are critical to modern performance, both at the exascale like Frontier and Aurora, and the laptop scale like I have today with my, I think this has a 2070 in the laptop I'm presenting from. And Chapel's GPU support, it's very young, but as we've seen in some of the previous talks, it is growing incredibly quickly to be a productive, performant, and portable language. And I think HPE and the implementer should be very proud of that. But we need to align ourselves to where the community actually is, though. We really need to pay attention to these high-level Pythonic ways of using GPUs, because there is a ton of energy and interest there. And you can go to any keynote this year, and you're going to hear a little bit about AI and data science. They're really the new federated frontiers for HPC. So I think that's something we need to be mindful of. And I think, as we'll see in the next act, that Chapel could really do a good job of filling the gap between the high-level library-driven Python and the very low-level post-serial GPU languages that we've talked about. So with that, we're going to start transitioning into Act 3, but I do need a drink of water. There we go. So next for Act 3, Chapel's role in our GPU future and our role as members of the community in Chapels. So I'm a really low-level, like crunchy GPU guy. I like to implement low-level stuff. So this is my attempt at zooming out and seeing some trends in AI and data science based on what some of my coworkers are doing. And to me, that looks a lot like a Jupyter notebook with some Python. There we go, Python inside. And that's where you keep your application flow, your bespoke kernels, and analysis and visualization. I see a lot of matplotlib. And that's an important part of these human thought loop workflows. But then when you need performance, you have to make this very jarring leap of faith and pick a library to do that with. And it's probably going to be PyTorch or TensorFlow or Rapids. And behind the scenes, it's probably going to be written in C++ and call out to CUDA, maybe HIP, and I'm not so sure about these other three anymore. And when you introduce that library, it does come with some questions. Now, all of your existing code has to interoperate with a library. That may require shifting your data into a format that's more amenable to the library. And this is not specific to Python. We see this in large C++ frameworks too. Sometimes they can be very rigid and require you to invest very deeply early on in their way of viewing memory. And that may or may not be a good thing. But even with the GPU performance that these intra-node libraries can do, it doesn't answer the question of scaling out to multi-node. So you're probably going to pip install another library that's going to wrap MPI or Spark or something like that. And it's very great that the installation process is so easy. We'll come back to that. But it does introduce yet more questions about how well this intranode piece is going to play with the intranode. And from my perspective, this all starts to look very interdependent and fragile. We see virtual environments that are sometimes gigabytes large. Sometimes there are mutually exclusive dependencies, so things get containerized and only talk through sockets. It gets pretty messy pretty quickly the more things you try to incorporate. So I think Chapel has a really nice opportunity here to help ease the path for these Pythonic flows down to parallel and then GPU and then distributed computing. So I want to leave the application flow up at the high level Python and Jupyter. I think that's a great place for it as an orchestrator, right? But I want a smooth ramp of complexity down to the GPUs. And I think that is where Chapel fits into the equation. Now, I don't want to get rid of these existing super powerful, high performance Python libraries. There's a lot of time and investment and knowledge state there, but I do want to wrap them in Chapel so that future users can use them directly from Chapel and retain interoperability with these libraries that they already know. But by doing the wrappers there, that would then allow them to write their bespoke kernels in CPU, then take them to GPU, and even to NUMA-aware or distributed through the use of colocales. And by bringing their bespoke pieces down into a language that can do both intra and internode and GPU pretty well, it takes away some of those opportunities for overhead and fragility to emerge. And then finally, I do I do want to kind of lower the analysis and visualization closer to where the data lives, because as we know, moving and transforming data is one of the most expensive fundamental operations in computing. So if we can bring the analysis close and visualization down into Chapel, that will let us do less, data transforming. So this is kind of the direction I've been thinking for Chapel going forward. And if you lean back and blur your eyes a little bit, it does start to look a little bit like what some of the other work we have heard or will hear about today, like Arcuda with especially the Arachne extension, as well as some of the talks that we're going to hear in session 5. So I'm really looking forward to the rest of the afternoon because it looks like other members of the community are thinking in a very similar direction to this. So to start wrapping up, though, we've got parallel and GPU hardware. We've seen that throughout Acts 1 and 2. And we've got a really solid parallel first GPU language in Chapel, and it keeps getting better every release. And we know that there's a lot of AI and data science energy towards using GPUs. And I think the factors that remain in our way as members of the community are these really sticky problems of inertia, friction, and exposure. And I like to think about those as 3 parts of a position equation, where position is your language share and inertia is where you are at. And I think old codes and languages, like some of the post-serial stuff we saw earlier, they're battleships. They're big, they're expensive, and incredibly powerful, well worth the investment, but they don't move except by committee. And transliterating those might be necessary in a couple cases to prove that our approach works, but it's really high level. It's really high effort. In the middle, though, is friction. That's what affects how quickly you can get new codes written in Chapel, right? And programming is not just about the language, which I think is very crisp. It's about the ecosystem around it. And we've seen a lot of really good progress here in the 2.0 push. But I think there are some unanswered questions in terms of installation and visualization and things like that. Because the ecosystem is really what helps or hinders your adoption rate. How easy is it for people to reproduce their existing workflows in our language? Or can they have an even better workflow? That's what we should strive for. And then finally, exposure is all about acceleration. The more people that you can get excited about your language, as we saw with CUDA, the better your long-term successes are likely to be, because more users allows you to better hone in on what your remaining friction points are and participate in feeding your own excitement loop. So I'm really happy to see some of the things we're doing, trying to reach into more communities. And so I briefly want to flip back to my CUDA lesson slide and sort of frame it in terms of these 3 things. Consistency it's all about they built their own positive inertia by doing the same thing year over year for 17, 18 years. They reached into the university programs to reach people like me before we learned something else, to expose us to CUDA before we got inert in OpenMP or something like that. They've consistently given away their tools. That's all about having low friction and high exposure. They welcome small fish, laptop programmers, right? That's casting a wide net and hitting all 3 bullet points all at once, because some of these laptop programmers are going to become HPC and AI engineers. And then finally, driving the conversation is all about exposure. So these things are compatible, and CUDA is a great example for how to attack them. And so before I wrap up, I want to briefly take the pulse on these. And I think we're doing okay on inertia, but we are learning and building on the shoulders of these post-serial giants. They're really not going to go anywhere. But I think Chapel's role is to grow as a complement to them. We have a much higher level approach, and it works really well as long as we can occasionally dip into some of these post-serial features. That's what I had to do when I needed CUDA device atomics before they were in the GPU module. And year over year, as we saw in the state of the language, we've increased the breadth and depth of Chapel codes. And I think most of our success there, and we could correct me if I'm wrong, is new codes and new users. It's not porting things that already exist. It's building things like champs from whole cloth. And we'll hear some more about new codes and extensions to existing Chapel codes in session 4. So I'm excited for the afternoon. And through rigorous at-scale successes like this, we're slowly chipping away at some of that negative inertia. But the last point I do need to hit is that while Chapel wins on clarity for maintainability, we do need more users so that there's a robust HR ecosystem, because it's not just about writing code. It's about being able to hire people that know how to work on it or level them up to work on it quickly. And so I'm hoping that some of the tutorials we'll see will also help with that leveling up part. On the friction side of things, gosh, just in the year and a half I've been here, the 2.0 push improved so many things, and I'm happy to hear about how much work is ongoing, including some of the stuff we saw in session one, like debugging and language server protocol tools. But there was some meme on Reddit a couple months back about where exe, the plight of these people who ended up at GitHub and really just wanted to download a binary. And I think we have a little bit of that. And I actually edited this slide live this morning because I was going to pick at installation a little bit more, but I'm happy to see some progress there. But I do think we need to work on our migration and in situ visualization stories because we don't have something like a matplotlib like Python does. But on the install side of things, compared to the existing post-serial languages, we're going to be getting deb packages soon. I was happy to see that. But if you want GPU, you're still stuck building from source. So the sooner we can take the single locale CPU deb packages and extend those for GPU support, the better. Because installing the language is the first great filter on whether or not people are going to be able to use it. If they choke there, that might be the last we hear from them. And that'd be a shame because I think we've got something really wonderful here. In terms of exposure, well, we're all here. We made it. And I'm really hoping the community survey shines some lights on how we ended up here. Because maybe we can build on those stories and leverage those opportunities to reach more people. I do think, though, as we discussed in Act 1, curricula are really the long-term answer. And to support a chapel-driven curriculum, we need to become just a little bit more general. And right now, this is part of inertia, but fortunately, there are other places to teach, and we're going to hear about that in Luca's talk in the next session, using online platforms to build a curricula for chapel. I think the third-party blogs are great. Independent credibility is fantastic for a language to have, and the social media push is great. But again, touching on some of those earlier Chew talks, we need to align to where users already are. And I don't have a lot of experience with Mastodon. I hope it's good, but there's a lot of salty programmers on Reddit. And unfortunately, our presence there could maybe use a little cross-posting. And in that vein, I think we need to broaden our scope a little bit. We've spent good time getting great HPC performance in HPC spaces, but everybody has parallel hardware now. And I think we would do ourselves credit by pulling in concepts and people from those more general spaces. So to wrap up this Act 3 with maybe some prescriptions, inertia is hard. It's real hard. It's strong and slow, and there's going to be a series of water puns that I hope you'll forgive me for. But small splashes are not going to move it. I think capitalizing on broader trends in the industry like GPU is where we could really start to make a difference here. I think friction which is where a lot of our work is going now since the 2.0 release, is a solvable engineering problem. And that's a great, really strong place to put our effort, both as implementers and users of the language. This is where we need to be contributing because we want Chapel and moving to Chapel to be as easy as drifting downstream. And when we do manage to attract new users, we don't want to waste their energy on turbulence. So improving all the stuff we did with 2.0, as well as our installation and visualization stories, an important part of doing that. And then finally, exposure is really important, but it's not a guarantee, right? We can show people the door, but they have to choose to walk through it. And there's a lot of competition for AI and data science devs right now, and they're going to languages that are very general. So anything we can do to improve our generality might help us attract those. And we need to reach into general spaces and show them that we truly do have a better path downstream. Because by focusing on these upstream experiences and newer users and their potential energy, I think that's what it's really going to take to shift the tide of languages towards parallel first through Chapel or something like it. Because, at the end of the day, every good cascade starts upstream. That's where it all starts. So in conclusion, as we saw in Act 1, the real world and everyday hardware is parallel. So I really would like it if we started acting like that. And that means using and teaching parallel languages in our day-to-day life. And in the second act, we saw a little bit of history of GPU support and how Chapel has grown incredibly quickly by building on those lessons. It's now productive, performant, and pretty portable. And I think we need to keep capitalizing on those trends. And we can do that by aligning ourselves and the language to this broader momentum towards AI and data science and GPU-driven approaches to that. Because Chapel really does have something nice to smooth that gap between really high-level Pythonic and low-level post-serial C solutions. So I think our best shot at growing a cascade is seeking general users and providing them a truly low friction experience. Reduce their barriers to entry and extend the amazing thing we built here to reach into the more general population and give them parallelism they've needed for a long time. So with that, I'd like to say thanks to the current and former members of the Synergy Lab. It is through exposure to all the interesting problems they're solving that I keep in touch with broader trends in AI and HPC. And I'd like to thank the Chapel team for inviting me to speak today, and about a year and a half of just really great discussions. I've had a lot of interactions with the GPU and IO teams, and they are just super motivated and really, really gracious when I occasionally blame them on something I've done wrong. And just great people. And finally, thank you to all of you all for being here today, being excited about this great language we've got, and continuing to fight the good fight on these three really tricky problems. I think we can beat them, but we're going to need to do it together. And in closing, this work was supported by the NSF Center for Space, High Performance, and Resilient Computing. And with that, I'll flip back to my conclusion slide for question and answer. Thanks for your attention.
Paul, great. Thanks very much. That was a very enjoyable and very informative talk, and I just loved the entire arc of it. So thanks so much. I have questions, of course, but I would love not to dominate the microphone. So let me start by just inviting the audience to raise your hand or jump on camera or whatever if you have a question you'd like to ask.
Well, I'm glad to hear my cascade pun landed.
And while waiting for that, I'll ask, let me just start by asking a simple question, more a clarification question than anything, which is when you were talking about sort of the education angle, I think you used a phrase like becoming more general or something about generality being important there. This was just a few slides ago, I think. I didn't quite understand what you meant by generality in that context or where you felt maybe things weren't quite where they needed to be yet. Is that something you could clarify?
Yeah, that's a great question. Specifically, it's been a long time since I took Intro to Programming, but I do a lot of in the console work. But one thing that I did an experiment that I didn't have time to fit in this deck is I think a lot of higher level workflows do involve an aspect of visualization, maybe plotting, but also, everyday programmers are doing things like windowing systems and OpenGL and Vulkan and things like that. And we can do that today through C interop, but you need to be good at both C and Chapel to do that. And if we want to be honest about fulfilling this, let's be more programmable than C and closer to Python, I think we need to recognize that those higher level users are not, the interop is powerful, but we don't want to have to ask that of regular users. So expanding the breadth of our standard libraries and our Mason packages and things like that is really where I think we could do this. And that might fall more on the community necessarily than HPE or the language implementers is, what things do we think are necessary? And for me, I think in situ visualization is one of those.
Gotcha. Okay, so yeah, back on the matplotlib point, which landed really clearly for me. Thanks. Other questions from others? Never know how much time to leave.
Yeah, it's fair. I have a couple difficult ones, maybe for the community, in case we don't, but I don't have good answers to them, if I'm honest. There's things. Yeah, you go ahead.
No, finish your sentence and then I'll go.
Okay. Yeah, I don't have good answers for them, but they're things that certainly come to mind when you're thinking about switching languages. It's, as a business, how easy is it to spin people up? If we give higher level approaches to parallelism, do we hide some of those concepts that students need to learn? What's our package management ecosystem like? It could be really good. I just haven't played with it, but I know pip is held up as one of the best examples there. And then there's always this conflict of, well, should I use a big C++ framework or should I just use a new language? So these are all difficult questions. I don't have good answers for them, but I think they're ones that we do need to be thinking about.
Yeah, great. I think it would be safe to say that your question about is Mason as good as other things, I think today I think we'd all agree it's not yet.
Okay,
Could it be? I think we believe it could be.
good.
And unfortunately, it's been one of those things that has kind of been backburnered for a lot of the 2.0 push. And we've recently just been doing a study to see like, okay, well, what would it take to kind of bring it up to snuff and try to make it more kind
Yeah,
of first class than it has been.
because like I was saying with the visualization and the interop question, I think there's a great opportunity for us in the community to help you guys out. If you give us a way to fill in some of these standard libraries or third-party libraries, we've got the talent. We can do that, and it doesn't need to all fall on you guys. And having
Yeah,
a good package management solution would help us do that.
right. Let me ask you a slightly bigger question than my first one. So I think, as far as I know, at least, I don't know that you have interacted with Arcuda at all, which again is our sort of it's client-server model where you're basically in Jupyter, you're in Python, you're doing sort of normalish looking things, but then under the covers, it's running in Chapel. And you did have a part of your talk that talked about sort of raising the level of abstraction, meeting people in Jupyter, things like that. It made me curious, like, first of all, to sort of verify, like, I think you haven't probably had the chance to kick the tires on Akuda much, if at all. But I was curious if you had sort of a notion of a killer workflow that would kind of go from sort of Jupyter Python all the way down to the GPU. Because I think on the other side, on our side, the Arcuda work we've done hasn't really linked up to the GPU work so far, but it has done things like link up to cool visualization libraries and things like that, basically by leveraging the Python. So anyway, I was curious if you had thoughts there or charges of like a great killer demo would be sort of, Jupyter, Python, Arcuda, all the way down to the GPU or something like that.
Oh, that's a good one. I have, yeah, you're correct in your assessment that I haven't gotten to do much hands-on with Arcuda. I'm not primarily a data science. I'm a low-level GPU kernel implementer.
Yeah.
Um, but I think, yeah, picking a high-level workflow in Python, it might be data science, it might be a traditional science, maybe something quantum, or an AI workflow. I'd really like to see a high-level Python AI workflow, some bespoke kernels written in Chapel, and then using, a PyTorch or something underneath with Chapel wrappers around it. So we mix existing libraries with bespoke code being written in Chapel so that it doesn't have to be C++, and is portable to both NVIDIA and ROCm that way. But I think that could generate some attention and say, oh, here's a portable AI workflow, Python for the client with visualization, scalable to multi-node through Chapel's locales, and then using something like PyTorch on the back end. Because I think we've got really good interoperability. It's hidden behind that C interface, so you have to know C to use it.
Yeah, that makes sense. I wanted to relay this comment from Luca, in case others haven't seen it or can't see it, and if they watch the replay. Luca says that he would add that faster compilation could improve adoption in education and research, since research is mainly an iterative trial and error problem. It's not a biggie, but would be a nice bonus. And of course, that's something we're working on as part of the Dino effort as well.
I would agree with that. I think I've seen some efforts that you all are doing on incremental and separate compilation, so I'm happy to see some fruit from that. And certainly you guys are way faster than some of the FPGA compilers I've used. But the closer
That's a
we
low
can get it
bar.
down, I know.
Yeah.
I didn't mean it in a bad way, but the
No,
closer
no.
we can get to like fast, instantaneous, it's all about feeding that human thought loop, right?
Yeah.
Um,
And then there's I think a question or prompt here from Wu Feng in chat. Visualization of your Jacquard similarity as it runs. Is that
ah,
a specific thing
um,
that you could speak to, Paul? Or
so that's a good question. You might be able to, I haven't touched Chapel Viz, but you might be able to use it to visualize some of the parallelism if we ran these loops on the CPU. But what we have cooking with the multi-locale multi-GPU version of that would be a great candidate for something that shows where the overlapped, hosted device transfers are, where the kernels are happening. Because the code as I built it is pretty hands off. It's pretty embarrassingly parallel, and there's a couple locks to make sure that people don't step on each other. But it wants to use Chapel tasks to let GPUs sort of run wild. And though ideally that will result in compute and communication overlap. And it'd be really nice to visualize that. And I don't know, maybe Chapel Viz could do that. Um, and
I don't know that
I,
it could today, but I think with more work, it
yeah,
could. And certainly that's something we've heard from, I would say, the Arcuda community as well, is they're used to coming from these very high-level Pythonic tools that give them a lot of kind of status bars and
hmm
utilization things. And, there's just a lot of visual stuff to look at to sort of have a
yeah,
sense of what's happening. We don't really have something like that today, but wouldn't it be cool if we did, right?
yeah. But I will say though, on the multi GPU like GPU timelines with data transfers and kernel execution and stuff, Chapel works really well with like NVIDIA Nsight Compute today. I've been very pleased with that.
Okay,
So good work there.
that's good to hear. I don't know that I was aware of that.
Um,
Great.
Several releases back, you all named GPU kernels in a way that made it much easier to tell which ones you were looking at in Nsight Compute, and that made a big difference to knowing where I was and wasn't losing performance. So good work
Gotcha.
there.
Cool, cool. All right, last chance for questions. Chris making me bear the burden of asking the questions today. All right.
Well, I
With
appreciate you
that,
keeping the conversation going.
Paul, thanks so much again for preparing this talk for us. It seems like you put a lot of work into it, and it shows. But again, thoroughly enjoyable. It's one I'm sure I'll be passing along to people like, oh, you should watch this talk. It's a real good one. So,
Fantastic.
thanks for the investment of time you put into making it for us.
Thank you all for giving me the opportunity. It was an exciting challenge.